Hello all. Today we'll be looking into the second topic, that is basically string matching algorithms of first module. So we have two algorithms of string matching, that is for string matching, that is Rabin-Karp algorithm and Knuth-Morris-Pratt algorithm. In short, we call it as KMP algorithm. So all of you know what are strings, right? So given, say, um, a set of characters like this, A, B, C, etc. Z. Say sigma is a notation for that. Then we say that any string member, that a string is any member of this sigma star, where star indicates 0 or more members. And suppose I write like this is a string. So you can say this particular example belongs to sigma star. And if we have another string like this is also a string, this also belongs to the same set. But when we have a string which contains not alphabets but numbers like 1, 2, 3, 4, and we can say it cannot belong to this subset, this set, because we have only space, alphabet A, B, C, etc. So only these are the characters that is allowed. So you can have either 0 or you can have more than 1 members, but not the characters that are not there in the set. Now, what are string matching algorithms? We know that we must have seen lots and lots of examples where string matching is required. Why? Because we are using Google search and maybe in a phone, autofills, and so many things are there. We are using so many text editing programs that needs to find occurrences of a pattern of the text. So typically you can say text is a document that is being edited, any document. And pattern is something that we're searching for, say a particular word that is provided by the user or given as input. So efficient algorithms that help in this matching is known as the string matching algorithm. Applications like text editing program, you're in your web browser, like in internet search engines and web pages to find some queries. Usually you'll have string matching algorithms taking place in the background. Even in biological concept, the DNA sequences is a sequence, it consists of several characters, and you can find for a particular set of pattern in the DNA sequence using string matching algorithms. So an example is just given here. Suppose that a pattern is given. This is the original text or the string, you can say, and a pattern is given ABA. So what we are asking you to find is you have to find maybe all the locations where this pattern occurs in this string. So you have to find the pattern. You can see there's a pattern occurring here, ABA. Then when we try matching this, but this is not matching. This is ABB. It's not there. Then you can find another A here. So we see whether it's matching. Yes, it's ABA. You can again find another match here that is ABA. So that I can see there are 3 occurrences of this pattern in the string S. This is an example of how DNA sequencing is done. So if you have, they may find some, like maybe for finding out efficient drug for some disease, or finding out patterns in the DNA which cause the disease, or if trying to find some patterns between that are hereditary in nature or something like that. So you can see these are the adenine, thymine, these are the characters which represent a particular protein in a DNA sequence. And you can see A, G, T, A, G, G. These are some of the patterns given. So how they have found pattern is just an example like this. And of course, our search engines, they all require string matching algorithms, because you start typing something, the similar patterns that you're searching for, maybe using some data structures like trees or tries or something like that. They'll be helping you finding the string that you're searching for. They'll give you options of the strings that are listed, like shown here. Then the basic algorithm that we just now saw how to match a string is a brute force approach. It's known as the naive algorithm, and we'll just go through it. So brute force algorithm compares the pattern to the text one after another, you can say one character at a time, until some unmatched, that is not matching characters are found. So suppose that the string 2 roads diverged into a yellow wood is the string, and uh, roads is the word we are searching for. Then what we do is we first come to the first character of the string and match it, try to match it with the first character of the pattern. And if they are matching, only we need to move forward and match the second character of the pattern with the second character of the string. But since they are not matching, what we do is we slide this particular word forward, one character forward, because we do not know what is the second character in the string. So we need to again see whether the second character in the string is matching with the first character of the pattern. It's not matching, so we again slide or move forward, and we found that again O and R are not same. Then we found a space maybe. So again we move forward, and finally we found that first character of the pattern and first character and one of the character of the string is matching. Hence we move on and find whether the rest of the characters are also matching. Say we got a OO here, then we got a AA, then DD and SS. So hence we found the pattern in the string. So the match is indicated by the boldface curve. So the algorithm can be designed to stop either after we find the first occurrence, or if the question is asked like you have to find the number of occurrences, then we need to search till the end of the string. Now, this is the basic pseudocode. We'll come to the algorithm. That is, the algorithm is given here. Show you an example. An algorithm is there. I'll show you when it comes to that slide. So this is a basic pseudocode. That is, we just match the text letter and the pattern letter to see whether they're equal. If they're equal, then we can compare the next character of the pattern to the next letter of the text. Otherwise, we move. That is when I said about sliding, right? So you move the pattern down the text, and that is forward. You move to the right. You move to the right of the text by one letter, and you keep on doing this until the pattern is found or you reach the end of the text. So suppose you're finding cat inside this sentence, school cat went over the fence. We found that there is a match in the first characters of both the strings in concern now. And but the second characters are not matching. So we slide one step forward and we found that then it is not matching. Again, it is not matching. And again, it is not matching. Then there is a space, it is not matching. Then we found a match. So when we found a first character match again, we check with the second character of the pattern, then third character of the pattern until we reach the end of the pattern. So we keep on doing this. If the letters, if at least one of the characters are matching, then we immediately go inside the loop and move on with the rest of the characters of the pattern. Okay, so that is the basic idea. Now, what is the complexity of this is basically, if you have, say, a string like this, and this is the total length of the string, okay, say n characters, and this is the length of the pattern, say m characters, then we can say that we do not, so once you reach maybe the last 5 characters, you can say avoid, but before that, we have to match every pair of five characters each, isn't it? We check with the first 5, and then we move with the next 5, then we move with the next 5, and so on. We keep on doing this again and again till we reach a limit like this. Because once it becomes less than 5 characters, there is no need to match because the length of the pattern is not equal to the length of the last few letters of the string. So then there is no need to match. So we can stop before that. So you can say the total number of, that is how many substrings will be checked will be, suppose the text has, I told you, n characters, okay, and the pattern has m characters. This is the text and this is the pattern. So, and we can say the number of substrings match. So from position 1 to the last character, when we are grouping it together, we can say it will be around n minus m plus 1. Okay, total n minus m plus 1. One character extra we always add, right? So you can extract a substring of length m. So we can say we have around, so starting from the first 5, then next 5 and so on, you will have around n minus m plus 1 substrings to be checked. Okay, that many number of substrings are there to be checked. Now, how many comparisons do we do per substring? So you can say for each of the substring, worst case, you will be comparing all the 5 characters. So that is why it is M. All the 5 means the size of the pattern is 5, right? So I told all the m characters. So the number of substrings that we are checking will be n minus 1 plus 1. And the number of comparisons we have to do per substring is maximum the length of the pattern, that is m. So what is the total complexity? You can say it is the multiplication of this into this. So it will be m into n minus m plus 1. So this is the basic complexity of this brute force approach or the naive algorithm. And if you talk about the worst case complexity, then we can say it will be at the most m into n, right? So because n minus m plus 1 is, you can say, maximum. The worst case, you can say it is just n, simply n. So we can say it is m into n. Okay, so that is what is written here. So in this case, maybe if m was 5, then we'll say 5 into, we don't know what is the length of the string we have to count. So whatever is the length of the string minus 5 plus 1. So we'll be comparing around 5 into n minus 4 times. Okay, so this is the number of comparisons required. Now, there are some notations to be understood in case of string matching. We'll see what are they. So a text will be shown as T1 to N. So if you have a text, then it is represented as T in square brackets representing the index of the first character. You can start from 0 also, it doesn't matter. Suppose they are denoting it as 1, then etc. N. So we put 2 dots basically to indicate from the first character to the nth character. So N is the length of the text or the string. Now, similarly, you have a pattern of length M. So the number of indices in that will be from 1, starting from 1 till n. So you can also have from 0 to n minus 1 or n minus m minus 1. So now suppose that so the elements P and T are characters. This is the basic definition only we have seen in the first slide from a finite alphabet set sigma. So we say sigma is either 0, 1 or it starts from A to Z, or it is only these 4 characters and so on. So now what happens when you are trying to search for a pattern? A pattern P is said to occur, we can say with shift S. Look at this bold S. In the text T, or equivalently, we say that the pattern occurs beginning at position S plus 1. Okay, so I'll tell you what it is. So suppose that S is a count starting from 0 to n minus m. Okay, or n minus m plus 1, you can say. Both are okay. So you can say S is between 0 and n minus n. So S, the value of S can be 0. That means you're not shifting anything. The value of S can be 1. That means you're performing a single shift. The value of S can be 2. That means you're performing a double shift and so on. So when we find a particular pattern, that pattern has an index from capital P is a name of the pattern or the array indicating the pattern. And we say it starts from 1 to m. And when it appears inside the text T, if this is the name of the string that we have, the original text, then we say the pattern occurs at a shift of S plus 1 till S plus m, because the maximum length of the pattern inside the text also should be from, say if you have 5 characters here, this should also be 5 characters. But we do not know where it starts from. So we need to know the offset value from where it starts. So that is this S, the shifting. Okay. So for example, suppose that this is a text. Okay, and this is a pattern A, B, A. And we are searching for a pattern. So you can say at this point, S is equal to 0. If you're starting sometimes in some of the textbooks, you can say they start from 1, in some of they start from 0 and so on. So in simple words, you can see here, what is a shift where the pattern match occurred of this pattern in this text T is basically 1, 2, and 3. Got it? 1, 2, and 3. So you had basically 3 shifts so that a pattern has been matched. So that is why S is equal to 3. So from the original text, you had to add 3 so that you get a shift of 3 positions And then finally, from the fourth position, you start a match. Or it can be like this also. Maybe you're starting from like this. You're starting from zero also, and maybe this is the third position. So wherever the pattern, so it depends on where, how your string and how your pattern indices start. Either it can be zero or a one. So depending on that, there will be slight change in this value. So when you do the algorithm, you can just check that. Okay. Okay. So this is a string matching problem where a particular pattern, we call this by this is known as a valid shift. This is very important if it is a valid shift or not. This becomes a valid shift only if then the pattern matches. Okay. So this is a basic complexity or the pre-processing time and basically the matching time. Two time complexities have been mentioned here. For the naive algorithm, there is no pre-processing time because you're directly coming and matching with the first character and so on. But the complexity is n minus m plus 1 into m, where n is the length of the text and m is the, earlier I showed you capital M and n. So just the same thing, small m and small. Now, in Rabin-Karp algorithm, there's a pre-processing time of theta m, but the complexity is almost same, you can say. And there's another algorithm here, but we are not using this. Then in KMP algorithm, we also have again a pre-processing time, and but very less, but much lesser than this, isn't it? So it's just theta of n, a matching time. So actually one of the best algorithms. So this is the naive algorithm or the brute force approach. Naive algorithm or the brute force trial and error method of a common string matching algorithm. A naive algorithm finds all valid shifts using a loop that checks the condition whether the pattern is occurring somewhere inside the text. And that somewhere starts from the position S plus 1 till S plus M. Okay. So for all the values from 0 to n minus m plus 1, there can be any value of s. So you just start from here. So for example, the initial one is if you have a text t and a pattern p, the length of the text is n and the length of the pattern is n for every value between 0 to n minus n. So I told you it varies whether you put a plus 1 or a minus 1, sorry, a plus 1 or you start from a 1. Both are almost same. The only difference is how you start the index. So when s is 0 to n minus m for in the for loop, we find out whether the pattern is occurring somewhere inside the string. So when you start in the beginning, s is 0, right? So 0 plus 1 is nothing but you're going from 1 till m. That's all, 1 to m. But after some time when s becomes 1, it will be 1 plus 1. 1 plus 1 means what? You start from 2 and then 2 plus m and so on. So you keep on shifting five characters we are looking, but initially we are checking the first two characters, say here and here. Then after that, we need to come to this character. So we check this and this. So this shift, this position will be the second character. Now this third position will be next time. It will be the starting from the third character. And next time it will be starting from the fourth character. So every time the value of S is changing from 0, 1, 2, 3. So every time you will be adding something. So earlier it was 0. So 0 plus 1, you started from the first character. When S becomes 2, it will be 2 plus 1, maybe 3, maybe 4, and so on. So this way we have to find the shift where it occurs in the original text. Now this is another example of the same thing showing the naive implementation. You can see at template is also shown how the pattern slides forward. Okay, so you can see the operation for pattern AAB. This is the pattern we have, and the text is given ACAABC. Now imagine the pattern P having a template that slides next to the text. All the images are shown, A, B, C, D, all the 4 images. You can see how it slides. So first, when S is equal to 0, we match the first two characters. So that is, we have P of 1 to maybe it is 3, right? So something like that. And if the index starts from 1 to 1, 2, 3, 4, 5, 6. So it moves on till 6. So this is how the text looks like. Okay. Now S is equal to 0. When S is equal to 0, we are directly matching these two. Okay. Then when S is equal to 1, we have to move forward. So S is equal to 1. So the next one will be T of S plus 1 till S plus M. Now what is the value of S? It is 1. That means we are matching the second character. So 1 plus 1 is 2 and this is 2 plus M, 2 plus 6. So you move forward until we need to move forward. So S plus M, sorry, it is M. M or M, it's not 6, it is 3. Sorry. So you have 2 plus 3. So from initially we check from 1, that is you had 0 plus 1 till 0 plus 3. That is you check from 1 to 3 characters. So these 3 characters we check. Okay. Then when S becomes 1, we are going to check from character number 2 to 6. So 2 to 6 means what? This is second character, this is third character, this is fourth character, and so on. Okay. Sorry, 2 to 5, 2 to 5 till less than 5. If it is less than, is given less than, or we just have to go from n minus m. Okay, that is either you can do like this or you can directly write this character. So whatever it is, you just go less than, only 3 characters has to be selected. Even if we go from 2 to 5, we just less than 5, if you write, you check 2, 3, and 4 only. Next time we'll be checking it 3, 4, and 5. Next time we'll be checking it and so on. Only 3 characters shift is given here. You can see. Okay, so the last length of the pattern is 3. So only every time from where you're starting, only 3 shift will be there. If you're starting from 3, then maybe you have to go till 6. If you're starting from 4, you have to go till 7, and so on. So depending on how many times you have to do it, that is the value of S. S has to go only from 0 to n minus m or n minus m plus 1, either of them. So S is equal to 0, there is no shift. But when S is equal to 1, you shifted 1 time. That is the meaning. When S is equal to 2, you shifted 2 times. When S is equal to 3, you shifted 3 times. Okay. So when you do the algorithm, you'll understand whether you need to start from 0 or you need to start from 1. So that is a basic idea of how a shift is calculated and how this representation is very important. That is, how do you write this? How do you write this? How do you can see that we are not writing character by character matching like in a C or in a C loop, which you have written. If you're coding or implementing it using C, we are not writing the step-by-step procedure. Instead, we are writing in a string-like manner where you try to write in a simple statement that P of 1 to M is equal means there is a one-by-one matching going on there, but it is not evident in this if statement. Then you have T S plus 1 and T S plus M. So this is the shift from the original position, S plus the original position, S plus the last position of the pattern. Okay. So only if there are 3 characters in the pattern, using the shift, there should be check of 3 characters in the text. So the shift value S keeps on changing, and every time we have a 3 character match in this case. Okay. Now what is the running time? Like I said before, n minus m plus 1 into m. And the worst case is basically you can say n into m also. Okay, now coming on to Rabin-Karp algorithm. So if you look at any, say, pattern and text, basically we can do something like this. Rabin-Karp algorithm was actually developed by those two peoples, that is Richard M. Karp and Michael O. Rabin in 1987. And the basic idea behind this is, you can say, it compares the hash values. You know what are hash values? We have already learned what is a hash value in data structure and algorithms. So rather than comparing the strings directly like you did before in a naive algorithm, we take some unique value out of a string. And when we compare whether the hash of the string that we have currently found out and the hash of the pattern, which we found out earlier itself, and we are trying to match those two hashes. If the hashes are matching, then only we need to check whether the strings are equal. Okay, strings means the pattern is available in the original text. So otherwise, we can save a lot of time. So that is how the Rabin-Karp algorithm works. The simple hash algorithm, I can say, suppose that you had a text of A, B, 6 characters. and you have a pattern of say AAB. Okay, say 3 characters. A very simple hash algorithm or a hash value that you can create. Say A is represented by the numeric value 1, B is 2, C is 3, D is 4, etc. etc. Now, how can you create a hash code of this? How do you create a hash code? A very simple is simply maybe adding all of the in numeric values of each of the character. So what will be the hash code of this? The numeric value is 1, this is 1, and this is 2. So if I can just sum all of them together, we get a hash code of 4. Okay. So we call it as a hash of the pattern that is nothing but 4. Now let us look at the text. What is the first 3 characters inside the text? We'll check the hash code of that. So it is A, Okay. First 3 is 1 plus 1 plus 1. What is the hash code 3? The hash code of this one and the current pattern's hash code, are they same? No, they are not same. So is there any need to match the strings? No, there's no need to match the strings. So we can move forward. So there is no need to match the string. So that is what the advantage of using this hash algorithm. Okay. Now, what is the next step? Next step is a slide to the next 3 sets of characters. Okay, there is no need to check anything else. So this sliding, every time you're sliding the window, first 3 character, next 3 character, and so on. And every time you're finding out the hash also. And like in a naive algorithm, once you find a single match of the character, we don't have to go and check the rest of the pattern. We are avoiding that step. There's no inner for loop, you can say. So just check the hash. If it is not matching, move forward. Okay. Only if you get a match of the hash, we have to check whether the characters are equal. So what do you have to do here? The next step is that is you can that is also known as a rolling hash function. You can check in the internet what is a rolling hash. A rolling hash is the basic idea. So for coming to the rolling hash, we need to know more concepts behind it. So we'll just simply see what is the rest of the way. But this is not a very good, what do you say, algorithm, a hash value, because if you simply add the numeric values, there's a possibility that some other characters also give you the same hash value. That is, when you in data structure, that is collision. We say collision, right? They all give you the same hash value. So it's known as collision. That is, here we call it as spurious hits. We'll see what is the definition of that. So now, another example, say where I can show you what is a collision is basically. Say we take another example. Let's clear this. Say you have a text A, B, C, D, A, B, C, E. Okay. The length of the text is this. And we have a pattern B, C, E. And the length of this is 3. Okay. Now, what is the hash of the pattern? We can calculate it beforehand. So it is 2 plus 3 plus 5, that is 10. Now, suppose for the first part of the text, I look at the first 3 characters. Let it be, we'll take the first 3 characters. We get 1 plus 2 plus 3, it is 6. So because 6 is not matching to 10, there is no need to check the pattern. Okay. Now, what is the next step that we can do? Next step we can do is check the next 3 characters, right? So how do you check the next 3 characters? So suppose that now it is A, B, C, D. We need to check the hash of these 3 characters. So you have to again find out what is the value for T, what is the value, because you can see in the previous example, we have already calculated what is the sum of A, B, and C, and B and C were already included in the previous step. And it is again repeating here. Now, what is the only difference here? The only difference is you don't have A, but you have a new character D. Got it? So this is known as the rolling hash. That is, instead of recalculating the hash of the entire string, we delete the first character and add the new character. So you delete the first character and we add the last character. So how can we do that in case of a rolling hash? We'll see. Now, say you have the value was, what was it? The total value was 10, right? So we have Basically, it is 2 plus 3, isn't it? And what is D? D, the value is 4. Okay. 10, okay, sorry, we have 6. Okay, sorry, we have 6. So this is basically 2 plus 3 plus 4. That is what we need to get the output. So we are ignoring this fact now. And what we do is, what was the sum of the hash of the previous one? It was 6, right? Now we need to subtract what? We need to subtract the hash value of A. What is the subtraction of the numeric value of A? It was 1. Now we need to add something, right? What is that? The value of D. Now what is the value of D? It should be plus 4. So that is 5 plus 4 is equal to 9. So basically we are taking the sum of the previous three. We are subtracting the first part's hash value, or what you say, the numeric value from the total hash, and then we add an extra value that is for the current letter that we we have newly taken into the window. So 6 minus 1 plus 4. So finally we get the value as 9. Now the original hash code value of the pattern is 10, right? So 9 is still not equal to 10, so there is no need to match. So I'll show you one more example. Let us move forward. So the text is A is now over, B, C, D, and the next one is A. So now we've checked ABC, then we checked BCD. Now we have to check CDA. Now you can see CD was already there in the previous step. And what was the total hash of that? It was 9. So 9 minus whatever is the hash value of B, that is say 2. And we have to add a new one, say 1. So we have the answer as 9 minus 2 is 7. 7 plus 1 is 8. Now again 8 is not equal to 10, so we don't have to check. Now let us check for another set of character. Say the next one is T is equal to A, B, C, D, A, B. So we have to look for DAB. DAB is basically 8 minus 3 plus 2, it is 7. 7 is also not equal to 10. Got it? Now let us look for the next one. T is equal to the next character A, B, C, D, A, B, C. After the AB, we are going to check ABC. Will it be a match? No, it will not be a match because the answer is, I think it will become 7 minus 4 plus 3. It will be 6. 6 is not equal to 10. Now let us go and look at the last one. That is A, B, C, D, A, B, C, E. Now BC is, this is the last character we have to match. So BC was already there in the previous step, which is a value of 6. So we got 6 minus, we have to subtract, reduce the 1 from that. And then we add a E. E has a value of 5, say. So we have answer 10. Now 10 is equal to 10, right? So because 10 is equal to 10, we need to match it with the pattern. See BCE, and this BCE in the text has to be matched, and we found that it is a 1-to-1 match. So hence we got the algorithm. So this is one basic way of doing it. Okay, this is a very simple example. But you can say that every time I'll show you another example, but you can see each of the sum here had different values. So you can say it was a very good example. But there are possibilities where when we take a character, say a string like this. Suppose you have a string of repeating characters CA, CC, AA, C, D, BA, etc. Okay, where n is equal to 11, and you have a pattern as DBA where m is equal to 3. What is the hash of this? 4 plus 2 plus 1 is 7. Now, let us check the first three characters. T is equal to CCA with DBA. What is C? It is 3 plus 3 plus 1. That is also a 7. See, 7 is matching to the 7 hash value of the pattern, that is 7. But is it a match? No. Why? Because the first character here is a D and here it is a C, and it is not matching. Okay, we're going to take another example. Take the second one. So the second set of, when you slide the window forward, you have a C, C, A, C. Again, we have a 3 and a 1 and a 3. It's again matching. But are the characters matching? Even though 7 is equal to 7, they are not matching. So again, they are not matching. You keep on doing this because all the sum of these is going to give you 7, 7, 7 again and again. So the repetition where there every time the hash values are matching, but the characters are not matching. then though that is known as a spurious hit. So what is a spurious hit? Basically, you can say it is a drawback of this algorithm. That is, every time you have a match in the hash code or in the hash value, but the characters are not matching. So we are actually, you can say, unnecessarily getting confused. So you can say there is a spurious hit. So you can say this can take a very what is a large complexity. So we keep on doing this until we get a match. And finally, you know, where we get a match is over here. Only these three characters are matching. Okay. So how can you make it better? Why this happened is because the hash value, the calculation or the function that we use. What is the function we use? Just simply adding the hash values. Hash values are what to say? You just simply adding the numeric value so that it generates a hash value. So what happens? There are other characters, the sum of which can generate the same hash value. So we need to have a better hash function which gives you different values. Then only you will be able to have a better match. So how can you do that is maybe one thing is DBA could have been written as based on this is the fourth character, the second character, and the first character. What can we do? We can maybe write it as in radix of the radix of this particular is 10. So this is the 100 position. So we can write as 4 into 10 raised to 2 plus 2 into 10 raised to 1 plus 1 into 10 raised to 0. So this gives you the number of 421. We separately found out the numeric values, right? But basically when you're reading it in a number, we call it as 421 and it is represented by this formula, isn't it? That is how we read it as 421 because this is a 100 position, 10's position and 1's position. So for each pattern, we can say we have a pattern like this. That is every pattern P of 1 into 10 raised to m minus 1. We can represent it in that way. Each letter in the pattern can be represented like this. The second letter can be represented as P of 2 into 10 raised to m minus 2 plus P of 3 into 10 raised to m minus 3, etc. Depending on the number of, because earlier we had in 421, we had 3 characters, right? So the power of this will be 10 square, the power of this will be 10 raised to 1, and the power of this will be 0. That is how we move forward. So here we used 10. If you have, maybe if you're using this, when you use 10, I was talking about numbers, right? But when you have maybe 26 alphabets, you can simply write into 26 square or something into 26 raised to 1, etc. or into 26 raised to 0. So you can also have a radix of 26. If you are using some ASCII value, maybe you can have 127 raised to into 127 and so on. So depending on what is the radix you require, you can have decimal or 127 or 26, etc. So basically, this is the entire hash function is generated, you can say, with the help of something known as a Horner's rule. So based on this only the formula of the Rabin-Karp algorithm works forward. It's another notation. We can say that any pattern starting from P1 to M of for a text can be represented as PM plus 10 into P M minus 1 plus 10 into P M minus 2 plus X. So you can see there is an inner bracket. So this is the outer bracket. Then inside that there is an inner. And this keeps on going plus, so etc. etc. 10 into P2 plus. So this is also there is a bracket. And then you have 10 into P1. The last one need not have any bracket because this is the last one. And then you finally close all the brackets. Okay. So this goes like this. Suppose I take a number 9847261. Now how this is going to work is the first set will be, you'll be multiplying the number with, say that you take the first one, it will be 9 into 10. So you can say maybe here 9 into 10, that will be 90. Okay. Then when you have the second number, so you will have the second number, you have to do one more multiplication with 10. Then only it becomes the next position, right? So you have 90 alone here. Then when the second number comes, you will have 90 plus 8, the whole multiplied by 10. See this one. This is 8 and this will be 90. Then the whole will be multiplied by 10. So into 10. So that will become 980. Then you take the next one. So that will be 980 plus, what is the third number? That is 4, the whole multiplied by 10. So that is in the outer boundary somewhere here. Okay, you'll have another 10 into for this. So this will be 90. This will be 8. So the total thing will be 980. Then next time you'll have 4 here. Then you have 980 plus 4 into 10. So it will be 9840. Then next time you'll have 9840 plus 7, the third character, fourth character, the whole thing into 10. It will give you 98470. 9847 into 10. So it will be 98470 and so on. So this keeps on going until you get 98471. So any number can be represented according to Horner's rule in this format. So this is the format I'll be using in the algorithms. Okay. So using this concept, we are going to do that the reduction pattern that we just learned now. That is when you're adding a row, performing a rolling hash, we'll use this formula and we'll be finding out a hash of this by using some appropriate means. And we subtract the first character and add the new character. And that thing has to be incorporated into this formula. So understood this much. I hope you understood this much. Now we'll move on to the algorithm. Okay, this is just an example showing, suppose that the hash value of A is 37 and AAAH is 100. Then when you match the hash values of the first 5 characters, we found the hash is different. So only one comparison is made there and we don't have to do character by character individual matching. We don't have to do because the hash itself was, it's not matching. So we slide the window forward like this and we found that again it is not matching. Okay, so how do you find the hash of this? Not by calculating individually one. We don't add or do an operation on each one of them. Instead, we try to find the hash by removing the first character and adding the last character. And this way we can easily calculate the hash that is known as a rolling hash. And we keep on doing this every time. And afterwards, finally, if somewhere here we found the answer. Okay. Now the algorithm, the basic idea of the algorithm using a pseudocode is given here. And this is the complete algorithm, the how to implement it. This is how we implement it. And we'll see what is the basic pseudocode. Just what I said now, the thing is just written in words. The pattern is M characters long, small m or capital M. And suppose that hash P is the hash value of the pattern P. Okay. And hash T is the hash value of the first M letters in the body of the text. So you have to find two hashes. One is the hash value of the pattern which is M characters long. Then we find the M characters because we have say 3 characters in the pattern and we have total maybe 11 characters. So only the first 3 characters have to be checked, right? So the length of the pattern will be the same as the string in consideration will also have the same length of the pattern. So that is why inside the text, the first M letters only have to be checked because we have to match the pattern. Now, if hash of P and hash of T are same, if the hash values match, then we perform a brute force comparison of the pattern. That is, if there is AAA here, we are going to check whether this also contains AAA. Okay, so then after that, we find the hash of the next section of the text. So next section will be the moving the window forward like this. Okay, we'll be looking at the next 3 characters with this pattern. So we move forward and next take the next 3 characters, say A, B, C. And we find whether the hash values, we come back here and find whether the hash values of the new are matched. So here there is a step where you have to calculate the hash. So that also has to be written. That is what occurs here. So you can say every time we started with the hash of the text as T0. Then after that, if we find a match, we have to find whether there's a brute force approach. We check whether one by one it is matching. Otherwise, the next step is finding the hash of the next three letters. So that is what is written here. Finding the hash of the next three. I'm just saying as an example, next M characters. So we'll be finding the hash of the next M characters. And this way, we keep on doing it until we are able to find a match. Okay. There's no condition of return. What if it is not matching? You have to write the answer. This is just a pseudo code. You have to write that also. Or we reach the end of the text. Okay. Moving forward, it's the same thing. This is the basic algorithm. And you can see the first step that we have to do here is find the length of the text. A text is given, then a pattern P is given, and a radix on which we are operating. It depends on what is our character set. Sometimes the question may be asked with alphabets, so it may be asked with integers also. So depending on that, you can change the radix. And because the entire thing is, what do you say, when you multiply and add, the entire thing can exceed the total radix. So what we do is we take modulus of this so that it's restricted. We take, you know why we take modes, right? You must have learned modular arithmetic somewhere. So we take a mode of a prime number q such that the values stay within a confined range that is less than q. Okay, because if you take mode of any value, say a higher value, a bigger value, so say mode 7 or something, the value will be reduced to values lesser than 7. It won't go beyond 7. So that is a so if you're taking a radix of 26, you can write maybe 25 or 26 here. Usually a prime number is preferred. So depending on it. So take a larger prime number, say 11 or 13 or something like that. Okay. Usually in the question, the prime number will be given. So n is the length of the text, m is the length of the pattern. And the first step that we do is find the hash, initial hash. By using the hash, we take the radix d. Say suppose the radix d in example that we're going to check is suppose 10. So we write 10 raised to whatever is the length of the pattern. Say you have three characters and we say 3 minus 1. And suppose the q value is also given to you, say 11. So we take 10 raised to 3 minus 1 mod 11. Okay, 10 raised to 3 minus 1 is nothing but 10 square. So 10 square is 100. So what you have to check out, what is 100 mod 11? 100 mod 11 is simply you just have to find, divide 100 by 11 and find the remainder. That remainder is what gives you the answer. Okay. Okay, so we'll just do this. 11, 11, 8, 9s are 99. So 9 is 99. So the remainder you get is 1. So what is 100 mod 11? 100 square mod 11 is congruent to, you can say, we say it's congruent to. It's equal to 1 under mod of 11. So we write a reduced value. So 100 is a value that is greater than 11. So when you take something mode of 11, all the values should be between 1 and 11. So it should be between 1 to 10, nothing more than that. Okay. So that is how we find the hash value. So this is a hash function they have designed. This is just like we did a hash function earlier, right? We just took the sum of some numbers. So similarly, you can have any sort of hash function. You can divide it with the not a prime number also. You can have mode of any other numbers also. But when you do a prime, the collisions will be less. Because why collisions occur? Because the hash functions give you the same value. Suppose the first set of characters gave you 7. Next set is also giving you 7, but they're not matching. So if you have a prime number, there's a possibility that the hash answers that you get will be off in a unique range. They won't coincide or they won't have a collision. Now, what is the first value of the P and T0 represents the hash value, this H, the same thing, the hash value of the, what do you say, the first pattern set and the first text set. So T0. T0 is the first set of characters. Then we move forward as TS and TS plus 1. We keep on finding for every shift. Okay. So without any shift, it is known as T0 itself. So when a shift starts, we say it as T1, T2, T3, etc. till the end of the string. Now, then the next step is we find out, initially we set the, sorry, this one mistake I did here. Oh, the balance was 10, right? So the answer we get here is 10. Okay. Sorry. It's 1 itself. This depends on the example you took. So it was 3 minus 1, right? So it's the same. Okay. Just 1 itself. Just ignore this. Now when we do an example, you'll understand it better. In our case, because I took the value of m as 3, I found the balance of 1 here. It is correct. Okay, now we'll check an example. So before going to the example, let me explain what are these for loops doing and then what is this. It's very important. It is basically what is written in this area in the pseudocode what I've written, the same thing. Here we're checking whether the hash values are same, right? So that part comes over here. The first step is you need to find the hash value. So hash values are stored of the pattern are stored in P and of the text are stored in T of S, where S varies from 0 to n minus n. So for the first 3 letters, suppose I'm taking a pattern which has a length of 3. Okay, imagine. So the first 3 letters, what you do is you multiply it with D. D is the radix, okay, plus P of I, where I varies from 1 to n. So this is this one slight change. You can also start from 0 because if your string is starting from the index 0, you can start from there also. It depends on how you label the string. D into P plus the character, the entire thing mod Q. So you keep on doing this in the for loop from 0 to m. And T0 is D is the radix here, it is 10. 10 into T0. What is the initial value of both of them? Both are 0. So here you have a 0, here you have a 0, and so on, mod Q. So you keep on doing this in the for loop, and finally you will get a value for P and you'll get a value for T0. The first 3 characters in the pattern, you get a hash value, and the first 3 characters in the text, you get the pattern's hash value, and for the that many number of characters in the text, you get the hash value, or that is enabled as T0. അപ്പം നമുക്ക് രണ്ടിനുമുള്ള hash value കിട്ടും. Now once you get that, you can see you come here where S is 0 and you get it moves till n minus n. You check whether the hash values that you got here are the same. That is what we have written in the pseudocode. If both are same, then you check by one. This is single equal means basically it is checking whether they are equal. So you have a double equal in actual coding, you can write it as double equal. So P1 to M and T, whatever is the shift you got. So here we had a shift of only 0 because we did not shift anything. We're checking the first set. This is the text. This is the pattern. We're checking the first set of characters, right? There was no shift involved. So S plus 1 till S plus M. Is there a shift with or without a shift? Are the strings or characters equal in the both the set of strings? If so, then we found a valid shift and we found a match. Otherwise, if S is still less than n minus m, that is your for loop still exists. Okay, S is initially 0. And in the next condition, if it does not get inside this, when it does not get inside this, when the hashes are not same. The hashes are same, only we check brute force approach one by one whether the characters are matching. The hashes are not same, then we come here and check once again, we check the condition, it is less than the total characters to be checked. And we find the next set of letters, the hash for the next set of letters in the text. And that is done with the formula like this. That is, we take the initial part, we subtract the first part of the hash, and we add the newer part of the hash. And the entire thing has to be multiplied by 10 here, you can see, so that it moves forward. So that is the basic idea. I said earlier, like we have A, B, C. So when you're checking A, B, C, we get a hash value here, right? And then when we're adding a new character, we have to subtract the hash from the total hash of ABC, we subtract a part of A and then we add a part of D. That is what is done here. We subtract a part of the first character and we add a part and we multiply it with 10, the radix whichever it is. And we add a part of the unit place. This is the 100 place, this is the tens place, and this is the ones place, right? Now, when you're shifting forward, this should become the hundreds place. So that is why we are adding an extra 10 here. Got it? And this comes as a newer ones place. So we add it simply as plus this thing. Okay, so that is the basic idea of this entire thing. Now we'll look at 2 examples and you'll understand it better. Okay, let us look at the example, the first one. Find the occurrence of the pattern string P is equal to 26 in the text string T is equal to T 31415269 using the Rabin-Karp algorithm and the module, oh sorry, it's not module, it is modulo. And the assume the modulo is or the mode is Q is equal to 11. Okay. So we'll see the example. 26. We have to check for 26 in the text. You know where 26 appears visually, we can see it's over here. So we have to check that many number of characters to get a match. So looking at the example, as a pre-processing part, look at the algorithm. Let's erase all this. Pre-processing part, you have to do these 5 steps. Okay, as a pre-processing part. Now, what are the steps we have to use? So initially we had 26 in the pattern, right? So suppose 26 starts at 0 and this is the one, the index 1. And the text is some larger character, say 3, 1, 4, 1, etc. Okay. And this also starts at 0, 1, 2, 3. If it is like this, then the length of the string n is equal to 9. And the length of the pattern is 2. Now what will be h? H will be d raised to m minus 1 mod of q. What is d here? D is given it is 10. 10 raised to 2 minus 1 mod of q, it is given as 11. 10 raised to 2 minus 1 is nothing but 10 itself. 10 mod 11. Any number less than 11, the mod value will be the number itself. So it will be 10. So in our case, the value h is given here. You can see we are using h as a multiplication factor here. So the radix is given here. So that 10 we have to use. Okay. Now what is the initial value of hash value of the string? Initially, we do not know the hash value of 26, right? So we put it as a 0. And then for T0 is the initial hash value of the string, the same number of characters. How many characters we have to take? Only 2 because the length of the pattern is 2. So for 31 also we do not know. So P and T0 both are 0. So these are the initializations. N is equal to 9, M is equal to 2, H is equal to 10, P is equal to 0 and T0 is equal to 0. Now what is the next step? Inside the for loop, you vary from I is equal to, you can move from say 0 to M minus 1. What is M minus 1? M is 2. So 2 minus, you just move from 0 to 1. Okay. We have to find out the value of P for the pattern. So once you find out P, it's never going to change. The hash value of 26 will be always the same. Okay. Only the text hash values keep changing. So how do you find the hash value? You have to use a loop. So you can see there is no relation between these two. So we can just we can complete one of them and then maybe do the second one. So let us see how it works. It is D into P plus PI mod Q. So it will look something like this. The hash value is nothing but D into P plus P capital PI, the character PI mod Q. So what is D? D is 10. The initial hash value is set as 0. And the pattern is given as 2, 6, right? This is P of 0 and this is P of 1. What is P of 0? It is 2. So we have mod Q. Q is 11. That is nothing but 2 mod 11, it is nothing but 2. Now that is not over. Parallelly, we have to find out T0 also, because the second step is finding out T0. We'll do it later. So, or we'll do it parallelly, no problem. Now, currently you can say I is moving from 0 to 1. And when I is equal to 0, this is what happens. And in this side also, when I is equal to 0, we have to find T0. What is the equation for T0? T0 is also similar. It is D into the initial value of T0 plus T, the first text value, mode of Q. This is the formula basically. You can see here, see? Okay. Now putting in the values, we get 10 into 0 plus the first character of the text. We'll write it here. This 3, 1, 4, 1, etc. So the first character is 0, 3, and the second character is 1. So you're going to look at 31 only. Okay, we are finding out the hash of 26 and we are finding out the hash of 31. So plus 3 mod 11. Now it becomes 3 mod 11. 3 mod 11 is equal to 3. So what is the next step? So is it over? No. What is the loop? The loop has to run 2 times till the end of the pattern length. What is the pattern length? It is 0 and 1. That is 2 times you have to run. Now when I is equal to 1, P will become the next one. That is the previous P was 2. So it will become 10 into 2 plus the second character here. What is the second character? It is the 6 here. So we have plus 6 mod 11. That is nothing but 20 plus 6 mod 11 is nothing but 26 mod 11. What is 26 mod 11? 26 mod 11. You can see 3s are 33, 2s are 22. So it becomes 4. So 4 is that. 4. Now, are we done with the for loop part for P? Yes. So finally, you got the hash of 26 as 4. That is done. Now we need to move forward to find the hash of 31 is not over. So T0 is not over. So we find out T0, the remaining part of T0. It is 10 into the previous value 3 plus the next character of T1, because I value is now 1, right? So T of 1 is what? The second character, that is 1. So plus 1 mod 11. Now what is that? It becomes 31. Can you see something here? What is the value that you got here? 26. What is the value that you got here? 31. That is, eventually we are extracting character by character. We are finding its correct place, tens place, ones place, adding it together. And finally, eventually, you're finding out the same character itself. It's just the formula that looks so this thing, but it's actually you're taking the first 2 characters of the string as well as of the pattern. Now we take mode 11. What is 31 mode 11? 31 mode 11, when we try to find out, we get answer as 9. So now once you find these two, what is the next step? The for loop is over. First set of for loop is over. Now we have to find the shift where a match will occur or not. So in order to find the shift, if we have to check for a match, the first thing we have to check is for S varies from 0 to n minus m. In our case, n minus m is n is equal to 9 and m is equal to 2. So 9 minus 2, we have to move, say 7 times or 8 times, we have to move the loop. So this P is equal to T of S. S is equal to 0. So currently, moving forward, S is equal to 0 to 9 minus 2. This is what we have to do, 9, 0 to 7. Okay. So if TS is equal P, that is what we are going to check. What is the value of S is now 0. So P, is it equal to P? No, because T0 is 9 and P is equal to 4. Since they are not equal, we can say that their hashes are not equal. Because the hashes are not equal, there is no need to compare the strings or compare the character by character matching. There is no need to do that. So what is the next step? Next step is we move forward. Only if they are equal, you check whether the character by character matching is there. And then we say that at a particular value or shift of this, +1, +2, +3, we found a match. Okay, then we can exit from this. But if it is less than n minus m, now what is the current value of S? S is 0. It is less than 7. So what we do is find out 0 plus 1. What is 0 plus 1? Find out T1, the next character. Now this equation, I'll just write it over here. Now, because 0 is less than 7, we move forward and find 0 plus 1. That is nothing but T1. Now, T1 can be found out by D into Ts minus T of current S value if there is a shift into the general hash equation. This is very important. Plus T of S plus M, a shift of the number of characters, the entire thing mod of Q. This is what we have. You will find in the algorithm there will be extra plus 1 here. Then in this case also there will be extra plus 1 because we are starting the index from 0. There is no need for that here. Now, what happens here is we are finding out T1, right? So the index, the radix is 10 and we have TS as 9. T0 is T0, right? T0 as 9 and we subtract the first part of this. We had 31, 41. This is how our steps go, right? So what you need to subtract? We were finding out the hash for 31. Now next we have to find for 14. 1 is common there, but the 30 part has to be removed, right? 31 is there and you have 14 here. So 1 is a common part here. So we have to remove the 3 from the tens place and add 4 to the ones place. So what we do is, what is the S character in here? S is equal to 0. So S character here, it was 0. This is text. The 0th index is 3. So the character at T of 0 is 3. Into the hash function value, we have found that it is just simply a 10. So this is how we subtract. See, what is the value? This the value is 30. That means you're finding out the 3 at the tens position. And then we are going to add T of S plus M. What is S plus M? Moving forward, S plus M means a shift of 2 positions, right? To S plus M. S is 0 plus M. What is M? 2. So 0 plus M is 2. So what is the character and the second position in the text? This is the second position. 0, 1, 2. That is nothing but 4. So we simply write 4 here. And then we take mod of 11. Now what is this? 10 into 9 minus 30 plus 4 mod 11. That is nothing but 10 into minus 21 plus 4 mod 11. That is nothing but minus 210 plus 4 mod 11. That is minus 206 mod 11. So negative 206. So that is one thing you need to know how to take mode values in negative sense. So it is basically finding out like it will be something like this. When you because you cannot have a remainder, when you subtract, when you normally take a remainder of this, you will get a negative value. Inside mode of 11, what are the set of elements under mode of 11? If you ask, it will be only from 1 to 10. You cannot have any negative values and you cannot have any value beyond 1 or beyond 10. Okay. So you cannot have a negative value here. So what is minus 206 mode 11? We know that when you look at the table, 11 into 18 will give you a value lesser than 206. But when you write a lesser value here and you try to subtract it, the greater value is the topper one, right? So every time you'll have a negative value at the mode. So what you should do it, you should have a greater value in the bottom like this, so that when you do a minus of this, this becomes a plus. Okay. Okay. So says you are writing minus 19. When you're writing minus 19, it will be minus 209. Okay, the value is minus 209. Now, how do you subtract it? Minus 206 minus minus 209 will give you a plus 209 here. So it is a plus 209 is the greater value and you have a minus 206 here. So when you subtract these two, because this is the greater value has a positive sign, you get a remainder of 3. So the answer of this one will be 3. Okay, minus 206. Another way of doing this mode operation is just simply add 11 multiple times to 206 and you find answer. And the value will be again negative. If it is negative, again add 11. You'll get an answer which is again negative. Again add 11, which is again negative. Keep on adding until you get a positive result. So that is the same because this is your adding 11 multiple times is same as multiplying it with minus 19. It's the same thing. Repeated addition is same as multiplication, right? So adding 11 till you get a positive value is the same thing that we're doing here. When we add 11 18 times, still we get a negative value. That is the meaning of it. But when 19th time when you're adding 11, you will get a positive remainder as 3. Okay, so 3 is the answer. Now, once you find out this, what is the next step? Okay, you found out the value for T1. T1 is equal to 3. Now, is the loop over? No. The loop is not over. You can see it is a 2if. So you come back here and you check whether P is equal to T of S, the new value of S. Now, what was the previous P value we got? The P value was 4, right? 4. And the current TS value, TS means here now the TS value is T1, right? So T1 is equal to 3. So are they both equal? One of them is 4 and the other one is 3. Are they equal? No. So we cannot go inside this loop again. Again, you move forward, find out TSS. The value of S is now, it was 0. Then it became 1 now. So 1 plus 1, it becomes T of 2. You have to find out now. Okay, now for that, we have to find out T of 2. I'll just show you one more example of how T of 2 works. Now T of the next time S is equal to 1, we have S plus 1, we have to find out. T of 2 is equal to 10 into 3 minus 1 into H. So you can see why it is 1. The text value was 3141, right? We found for 31 first, then we found for 14. Then we're going to find for 14 and this way. So 3 into 1. Next, we have to add this. So remove this extra 1. Now we have to find for 41. So add this 1. So 3 minus 1 into 10 we do. Then the entire thing we have to add the new character. What is the new character here? It is 1. The entire thing is mod of 11. So it becomes 10 into 3 minus 10 plus 1 mod 11. 10 into minus 7 plus 1 mod 11. It is nothing but 70 plus 1 is minus 69 mod 11. Minus 69 mod 11 is 8. So how can you find out? I'll just show you one more example. 11. So you have, if the closest one is minus 6, right? So if you write minus 66 minus 66 is going to give you a negative answer. We cannot have that. So you multiply it with minus 7. Now it becomes 77. So minus will give you a positive value here and a negative value here. So the remainder will be 8. It's a positive 8. So the answer will be 8. Okay. So now once you got T of 2, what was P? P is equal to 3 and T of 2 is equal to 8. Again, we come back to the loop here. So without doing anything, we're only moving forward, calculating the hash, matching the hash. If it's not matching, again, move forward, find a new hash, calculate it. So you keep on doing this. Sorry, P is equal to 4, right? So sorry, we can check here. P is equal to 4. Now 4 and 8 are not matching. So again, we move forward, find out. We found out for 31, then we found out for 14, then we found out for 41. Now you have to move forward and find for the next one. Remove 4, add the new one. So we keep on doing this until, so what is the total? Look at the example that we are looking at. See this 3, 1. We do for 31, we do 14, then we do for 41, then we do for 15, then 52, then finally 26. So when it comes to 26, we'll find out that the hashes are matching. So in a special case, you can see when it comes to T of 3, T of 3, you get a value of 4. I'm not doing the entire example, so you can find out when you do T of 3, that is 2, when S is equal to 2, the value of T will be S plus 1, that is 3. You'll get an answer of 4. Now 4 is matching to 4. That is maybe for this one. 15. For 15, I mean. For 15, you'll get a hash function of 4. but you know that 26 is not equal to 15. So you can say that it is not, it's a what you call it? You call it as a spurious hit. Okay. So then for T of 4, you get 8. You can check it. T of 4, you should get a 8. T of 5, you should get a 4. Again, it is a spurious hit or no? No, it is for 26 itself. So T of 5 is where you get the answer. For 26 matching with 26, where that is the T of 5 step, fifth step, and so on. Then you move, check forward for T of 6, T of 7, etc. You get different values. And finally, the loop will end when will the loop end? When S is less than equal to N minus N. So when it is less than 7, you can stop. So it will go till S is equal to 6. When it becomes S is equal to 7, you can stop. So this way you found a single match at the fifth shift. Okay, so that is a basic idea. You had a shift of 5, say 1, 2, 3, 4, 5. This 5 shift, and then you got the answer. From the 6th onwards, you got the answer. Okay, so this is a basic idea. Hope you understood. Please try to do the second example. Thank you. Okay.